So we do have this rotating quad, and last time I wanted to add some camera movement with SDL, but I kind of decided that this is a bit boring. So I wanted to explore loading models and showing those instead of hard coding some positions and vertex coordinates in the vertex buffer. And with models there are multiple formats, of course, that you could use, and one very popular one is GLTF, which is a full-fledged 3D model transfer format, and it supports a lot of stuff. It supports hierarchical nodes, meshes, textures, and like even animations and even skeletal animations, so like skin meshes. And this is a really good format, but it's also a very complicated format. If you want to use that, you probably want to use a library called CGLTF, and thankfully Odin has bindings for that in its vendor collection, so that is covered. However, it's not something that we can quickly do in our project because GLTF definitely requires some structure, some notion of objects and scenes and transforms and whatnot, which we don't have. And I just wanted to load something to show instead of hard coding. So there is another format that we could use, and this is the Wavefront OBJ format. It's a much easier one, and because it is easy, people often use it for prototyping, so that's what we are gonna do. So there's this guy, Kenny, right? He's very popular for his assets that is free for everyone, and he makes some 3D models which are really cool. So I've downloaded this car kit, and let's try and load some of those assets. If you go into this model folders, there are different formats like FBX, GLB, which is GLTF binary, and OBJ. So OBJ is this very simple format which we are gonna use. So let's see. We can look at the overview and choose some, maybe the sedan sports looks nice. So we go into the OBJ folder, find it, sedan sports, and just copy it into our project, right? And also it has a texture which we'll use. It's a very simple texture, but it's an actual proper texture. So now if you actually look at this OBJ file, you can see that it's basically a textual file, and it's very, very simple. So the most important parts here is these V lines, which are basically vertex position definitions. The first three numbers is position, and the last three are actually optional. I don't think they are even part of the OBJ format, and these are colors. So, but here it's just white, so we're gonna ignore it. Then the second important line here is this VT, which is a vertex texture coordinates. So basically this is a bunch of texture coordinates to use. There's also VN, which are normals, which we will not use for now because normals are normally used for lighting and shader effects and maybe collisions like in physics and stuff. We are not at that stage, of course, right now, so we are not gonna use that. And the third most important thing that we want to parse here is this F. F is basically a face, and in original OBJ specification, a face can be whatever. It could be a quad, it could be like a polygon even, but I think most of the 3D software just exports triangles like this nowadays. So basically each F line is a triangle, and each element in this triangle is a triplet of vertex position index, vertex texture coordinate index, and the vertex normal index. So we are gonna read this and just use the positions and normals. So how to parse this? Normally, if you want to do this really properly, you would write something called recursive descent parser, which is a very, very straightforward and performant way to write any kind of parser for textual data. But I actually found a more dumb and a bit simpler, maybe, to understand way to parse it, which is just split the whole file by lines and then split all the lines by space. and in the case of faces, also split by the slash. This should work. Thankfully, Odin has this strings package in the core that provides everything that we will need for that. And also the API is pretty cool because it supports this iterator variants like split by byte or split by line iterator, which are actually not allocating at all. They just mutate the strings. So the strings in Odin are kind of like slices, except that instead of having a element of the same size, like with bytes or whatever, it contains Unicode characters, which can be either 1 or 2 or 3 bytes long each. But thankfully, if we take a look at this file, we see that it only uses the very basic ASCII character set, like numbers and Latin letters. If we use only the first 127 characters, then the UTF-8 format will just use 1 byte, just as if it were an ASCII encoding. So this is nice, which means that we can just split by bytes and check bytes here, and it will work. So that's my plan. Let's maybe write a parser for this. Alright, our main file is kind of huge already and not very well structured, so this is something for the future. We should probably give it some structure so we have some space to expand it. Thankfully, the OBJ parser we can actually start creating in a separate module. So let's maybe create a new Odin file like obj Odin. Let's have it in the same package as main, so package main. That basically means that it's gonna be in the same translation unit as main, and all the types and functions will be available between obj and main, right? Alright, now let's define the data structures that we will need to represent this file. So we have vertex positions, vertex texture coordinates, and face indices, right? So let's create a structure for the obj data. It will contain positions field, which would be just a slice of vector 3. We do have this type, but it's actually defined in the context of the main function and not in the context of the package. So maybe we should move this out, just place it somewhere here, it will be available. Then we have our texture coordinates, let's just call this UVs. That would be a slice of vector 2, which is the type that we do not have, but we definitely use it in our vertex data here, right? But we use it directly, a pair of F32, so maybe let's introduce a name type for that, vec2. Let's move it here. And then we would have a list of faces, which would be a slice of a pair of position index and the UV index. So let's maybe create a new type for that, something like obj face index. Something like this, and that would be a position index and UV index. Maybe these two should be uint instead of int because it's an index. Alright, now let's define the procedure to actually load the file. So obj load procedure, and that will take a file name of string and return an obj data structure. So as I said, we're gonna using the strings package. We're gonna import this or strings. First we want to load the file into the memory, and this is something that we are gonna do using the standard OS package. There's actually two versions of OS and OS2. I don't know the status of OS2, but I think this is a new version currently that will replace OS at some point, but yeah, let's just use the normal OS, which is supposed to be stable. So we would use OS read entire file from file name, which does exactly what it is called, and that takes a file name and returns a pair of data and success boolean, like a lot of things in Odin. So that would be our data and whether it's okay. And as usual, we don't really handle errors in our Hello World project, so basically we just assert that it was okay and hope for the best. So let's make it compile for now, and maybe add a call for that somewhere in our main, so we can quickly test what is happening here. Maybe somewhere here we can say we want to load our beautiful sport car model. Alright, but as you can see, that returns a slice of bytes, but as I said, strings in Odin are actually just also a kind of slice of bytes, except that each character can consist of 1 to 4 bytes, so we need to consider that. But anyway, what we can say is input string equals just a string of our data. So this case should work. Maybe we can just print this by basically logging it into our console. Log debug input string. Let's see what happens. Yeah, it's logged. Nice. So now we're gonna be using this split lines iterator, which is a non-allocating iterator over the text that basically splits the text into lines. And how it works is you pass a pointer to a string, and that would return you a line that it would extract, so the line before the end of line character, and whether there was a value, right? And also it will mutate the value in given s to the rest of the text, so after the new line element. And then next time we call this, it will do the same, and until the OK is false and there's no new lines anymore. So this is pretty neat, and this pattern here, the value and OK, is something that Odin can iterate on with a for expression. So this is what we are gonna use. We can say for line in strings split lines iterator, and we just pass the input string like this. We can maybe also debug the lines themselves and see, indeed, each line are logged separately. So what do we do now? Well, basically we want to skip all the lines that are empty or all the lines that do not start with what we want. So this grouping that we can afford not to care about, this material references, the comments, all of that we can safely skip. So this is what we're gonna do. So first thing we're gonna do is skip the empty lines, which would mean if length of the line is 0, then continue to the next line, right? Now, this is not a proper parser, of course, it's just a very minimal parser that will extract what we exactly need from this file. Maybe you should trim the white spaces, and maybe you should actually parse these groups and normals and other stuff that is defined by the standard, but we will not do it here. So this is how we're gonna skip the empty lines. And then for the actual lines that we want to extract, we will simply switch by the first character. So switch line 0. That will give us a first byte in the character. As I said, because we are using a simple ASCII encoding here, that should work with UTF-8 strings as well. So we can say case v in single quotes, which would be literal for a byte, parse v and vt, right? Then we would say case f, parse f. Now, how we differentiate between v and vt? Well, we simply switch on the second character here. So switch line 1, and we simply check if it's a space, then we parse position. If it's t, then we parse UV, and this would be a parse face index. Alrighty, but what does parsing exactly means? Well, we're gonna call some function on this line that will return us a vector 3 for position, vector 2 for UV, or face index for the face. And we will add them to an array and then just return as part of this obj data. That's the plan. So let's maybe create an array of positions. That would be a fully dynamic array, so we would use make function and say dynamic vec3. Then we do the same for UVs, so instead of vec3 that would be v2 and the name would be UVs. And finally we do the same for faces, so we would say faces equals make dynamic array of obj face indices. And we can already return them here, so we don't forget to do this. So basically what we do is take those and return them as part of the object. Except that we cannot really return dynamic arrays as slices, but we can easily make slices out of them by using this slice syntax. So basically this would be a slice of the full length of the dynamic array. Now, before we forget about this, because this is dynamically allocated and reallocated, we want to free the memory. So we want to provide a function to actually destroy this stuff. So let's just write it right away. Obj destroy. It is just a procedure that takes the obj data. So maybe obj data. And yeah, we simply say delete obj positions, UVs and faces. So that is done. Now let's maybe write the usages for all these parse positions. So we would say pos equals some parse position, and we will pass everything after the v and the space after it. So that would be a slice of line starting from the second character. So right, the v would be the 0th character, the space would be the first character, and whatever comes after would be the second character. And then we would just use an append function to add it to an array. So for UVs we would do the same, something like UV equals parse UV. Instead of a slice starting from the second character, we would pass a slice starting from the third character, because we have 3 characters as a prefix here. So we would say line 3, like this, and then we would just append it to the UVs array as a UV. So let's maybe start already implementing this. So we define a parse position procedure that takes a string and returns a vector 3. Now the string that it gets is basically a space separated sequence of numbers, and to extract a substring separated by space there is a handy function called split by byte iterator, which works exactly like the split lines iterator, so it doesn't allocate and instead of just mutates the string in place. So we can easily just iterate over the parts here, but iterating with the for statement would actually be a bit awkward in this case, because these are not the same type of elements, right? This is x, this is y, and this is z, and this is something that we don't want to iterate at all. So one easy way to actually use that outside of for is just call this as a function. So let's do exactly that. Let's say x should be strings split by byte iterator, and that should take a string, and the separator byte is space. So this is all and good, but there are 2 problems with that. Well, first is that this actually returns x and OK, and as usual our error handling is non-existent in this project, so we just assert that it was OK. The second problem is, of course, that it takes a pointer to a string and not a string because it wants to mutate it, and it still complains that you cannot take the pointer of a procedure parameter, because procedure parameters in Odin are actually immutable, which is most of the times actually what you want. So what we will do here is introduce a local copy of the procedure parameter, which we can mutate however we like. Just like this, we can use the variable shadowing for that. That will work just fine. So repeating this is a bit annoying, so maybe let's extract this into a function, something like extract separated or something, right? And we will pass a pointer to a string, so just like this, and a separator, which would be just a byte. That would return us a substring, so just string. So we simply take this, we say substring and OK, split whatever we pass, it's already a pointer, by a separator. Then we assert that it was OK, because that's our error handling, and then we just return the substring. And now we can simply use our extract separated method to call it multiple times and extract values one by one. So on the first call it will extract this part, then this part, then this part, and we will not actually call it for the color because we will not use this. So what we do is simply x, y, and z, and then we would return a vector 3 of x, y, and z, right? Except that those are still strings and we want to convert them into F32s, right? And for that, Odin has of course a standard package called strconf, which provides a bunch of string conversion methods that will do exactly what we want. So let's take a look at it. Somewhere here there's a method called passF32, which basically takes a string and returns the parsed value and whether it could actually parse it. So let's handle it as gracefully as we do here by asserting, so maybe just have a local parsef32 version. That would be a procedure that just takes a string and returns an f32. So that will call the strconf function, so res OK equals strconf parse f32, pass the string, assert that it is indeed OK, and return the result. Now we can simply wrap our calls into our parsing function, so something like this, and hope for the best. So let's maybe comment this out and just log debug the position. As you can see, it seems to be parsing correctly, so this works. Let's uncomment our parse UVs and implement this exactly the same way, so we can actually just copy paste this, call it parse UV, and that would return a vector 2. We can remove this, and maybe we could rename those to U and V. Check the error here. Okay, there's a typo, that should be UVs, not UV. And it still compiles. This is good, so now we can actually parse the face indices. So the face indices are actually interesting. So we have a flat list of faces, because this is what we're gonna use in the end, but each line has 3 vertices with indices to the positions and UVs, which means that our parse face index should return actually a triplet, so 3 values of obj face index, and then we would just append all 3 of them to the flat faces array. So let's maybe write a function, something like indices equals parse face, pass the line starting from the second character, and let's define the function here. So parse face proc s of a string, and that will just return 3 object face indexes, right? Now let's quickly append it to the faces. Thankfully, Odin has a nice function called append elements, which is a function that allows you to append any number of elements to an array, which is nice. So faces indices 0, 1 and 2. That should work. Now, what do we want to have here? Well, we basically want to do exactly the same thing as we did for parsing positions, which basically would be splitting by space and then parsing each element. So this is exactly what we are gonna do. Exactly like here, we would say S, we want a mutable local variant of that. And then we can simply just return our slice of 3 face indices. So we would say something like return, then we would like to extract separated, and each element we would say parse face index or something like that, and we just duplicate this 2 times more. So we have 3 elements here. Makes sense? So we basically extract the first part, then the second part, and the third part, and then we just pass them to the parse face index function. This parse face index function is something that we still need to write, of course, so that would be another procedure that takes a substring and returns a face index. So obj face index, which, if you remember, is just a pair of position index and the UV index. So let's write that. So basically it's another extraction of elements separated by slash this time, but instead of a f32, this should be a uint. So let's maybe have a function for parsing uints. Just like this, we can copy paste it, call it something like parse uint, and change this to parse uint here. Of course, the return value should be also uint. And now let's just use it in our parse face index function. So basically we do exactly the same. We have a local mutable string, then we extract first 2 elements here and parse them as int. The third part is the vertex normal that we are not using right now, so we will not extract it. So let's simply return a position that would be parse uint. From the extract separated result, we pass the pointer to our local string, and the separator would be slash this time. This would be EV. Now, one important thing to consider is that indices in Wavefront OBJ files start with 1 and not with 0, but we actually want to use this as an index in our position and UV slices, so let's just subtract 1 from both of them. That would be our index. Still compiles. So yeah, that should be it. One thing that I completely forgot about actually, and this is very important, that we actually never free this byte array that we use. So we do have an object destroy function for our object data, but the actual file data is never part of it, and we never actually destroy it. So maybe we should use the normal Odin idiom and defer deletion, so delete, of data as soon as we exit the scope, so this function, right? That should work. Alright, before we actually try to make vertices in indices from this OBJ data, I wanted to actually check if the data is loaded correctly. And printing it out is maybe not a good idea because there's a lot of data. So I wanted to attach the actual debugger to our Odin program and inspect some values. So with debuggers, there are multiple options. You can use something like RAD debugger or RemyDBG, or you can probably use any other debuggers, LLDB and whatnot. One very simple way in Windows with VS Code is actually to use this C++ extension that includes a debugger based on the Visual Studio debugger. So this is what we're gonna use. So let's just create a new launch.json file, which is a debugger configuration for VS Code. And here you can see the C++, Windows or LLDB, GDB selection. I will choose Windows. It might happen that you don't have this in the menu, which means that the extension wasn't activated, because I think it normally just activates when you open a C file or C++ file. But what you can do is just basically write this out by hand, and it works exactly the same. It will activate. So yeah, let's just call it just launch, type cpp vs dbg, request is launch, and the program would be our program, which is hello SDL3.exe. Arguments are empty. The working directory should be our just workspace folder, and all the rest we don't care because we can leave it as default. One thing that we probably want to do here is build our application before launch, just to ensure that it's the latest code running. So for that we can use the pre-launch task. That would be something like build. We only have build and run, so let's maybe go to our tasks JSON and just copy paste our build and run function, remove the run part from the label, remove the run argument from our build bat file, and remove the default group. Of course, if you are using any other editor or any other build tool, that would be up to you, but this is what I use, so let's do that. Yeah, just make sure that you specify this -debug argument for the Odin compiler so it generates the debug symbols database here. So now I think we can just set a breakpoint and launch the hotkey as F5 for VS Code, and it will stop here. You can see that we have a lot of local variables, which is a bad sign. We should really restructure our code by now, but this is for the future. So let's try stepping through and looking at the OBJ data. So one problem with that debugger is that it doesn't really understand Odin slices. With something like red debugger, you can actually specify that this is a slice and it will show it to you correctly. But for now, we can just see that the first element at least is filled with some sensible data, the same for positions, the same for face indices. We can actually check that this 2 is actually 3 minus 1. Remember that we're subtracting 1, and this 1 is 2 minus 1. So this works, and we have 1000 positions and 127 UV coordinates and a lot of face indices. So we have our object data loaded now, and we have this data structure which has position, UV coordinates, and the indexes for positions and UV coordinates. And you would think that this actually maps well to the vertices and indexes buffer that we have. So you could construct the vertex data out of positions and UVs and then specify the indexes from the face index. The problem that this is not the case. OBJ is actually a very old format which was designed before the modern graphics APIs, and it's not very usable directly with that, so it's not very fitting. It only really works well with this kind of prototypes that we are writing here, not for production. For production you would probably would use something like FBX or GLTF or just your own optimized data format. Anyway, the problem is that for indices we want to have one index that points to a single vertex data structure. However, with the face index we have two indices that can be different. And this is a problem that is actually not very easy to avoid, and what we are gonna do is simply generate a vertex per each entry in the face index, which would lead to a lot of duplication, so a lot of duplicated vertices and UV coordinates, but this is fine for our prototype. So basically what we want to do is generate these vertices and these indices from our OBJ data. So let's move the byte size calculation a bit to the bottom, because that will not change. It will work for dynamic vertices and indices just as well. And let's change our vertices and indexes to dynamically allocated slices. So make vertex data, that would be a slice of size, which would be a length of OBJ data faces, because we are generating a vertex per index. Maybe we should have named faces indices or something and not faces, but it's fine. Now for indices we would do exactly the same. We would just create a dynamic slice of the same length. Now to fill it we just simply iterate over our faces and fill the elements. So for face, then we will need an index of the face. In OBJ data faces, we create a vertex data at this position, so vertices I equals a structure with position, color, and UV. Now the color is something that we don't take from the obj file, so this would be just white, and position is something that we should take from the positions array using the index that is provided in the face. So this is exactly what we do. Obj data positions face pos, and we do exactly the same for UV. So obj data UVs face UV. And for the indices, we simply pass the index itself, casted to U16, of course. That should be basically it. Let's run it and see what happens. Well, I don't know if you can see it on the YouTube with the compression, but there's only like a small weird triangle flying around instead of a full model. And the reason for that is that we are still hardcoding the number of indices that we draw to 6. So basically we draw just 2 triangles of this model. And what we want to have is, of course, draw all the indices that we have. So let's maybe introduce a num indices, which would be, of course, just a len of indices, and pass it here to the draw GPU index primitives instead of 6, and that of course should be U32 because SDL API. Before we actually run this, let's not forget to clean the memory that we allocated for obj data and vertices and indexes. These are now dynamically allocated slices, so we should get rid of them. It doesn't really matter for this program because, of course, the lifetime of these vertices and indexes is basically the same as the lifetime of the whole program. But just to make a habit, we should probably free the memory as soon as we don't need it. So let's see, the OBJ data is something that we can actually destroy as soon as we have the vertices and indexes data filled, right? So let's just call obj destroy obj data. And vertices and indices is something that we can free as soon as we upload them to the GPU transfer buffer, right? So we can basically just delete them here, indices and vertices. Now let's try to run this. Yeah, that seems to resemble the car, but there are multiple problems with that. First, we are using the wrong texture here, and second, you can see that we can look at the car kind of like through an X-ray. This has to do with depth buffering, and this is something that we are gonna tackle in the next video. So stay tuned.